Okay folks, so here we go again. So this is the go through for the mechanics questions. Probably managed to start here with the hardest question I think of the 15. So we've got a car with a useful power output of 6.5 times 10 to the 4 watts. It's got a mass of 950 kilograms and it's moving up the hill at a steady speed. The slope of the hill is 12 degrees to the horizontal and it's got no resistive forces. Now what that means is we can ignore friction, but there are forces of course which are stopping it going down the hill because part of its weight stopping it down the hill. If we draw the actual forces on here, so there's the force of weight, so 950 G going vertically downwards, there's the reaction force off the slope, and there's some force from an engine which is making it go up the slope. What we need to know is if this is a steady speed, the force down parallel to the slope must be equal to the force up the slope. So we need to take this 950 G and resolve it into its two components. So it's got one component here which is equal to R into the slope, and it's got a second component this way which is parallel to the slope. This angle here is the same as this angle, so this is the cos bit, this is the sine bit. So the two parts of this resultant force, this one is 950 G times sine of the 12 degrees. So what we can tell from that is that the force down the slope, which is equal to the force up the slope, same magnitude as the force up the slope, is 950 times 9.8 times the sine of 12 degrees. And that force comes to 1935 newtons. So in order for the car to go up the slope at a steady speed, it's got to satisfy this equation. The power is the force times the velocity. So we know the power is 6.5 times 10 to the 4 watts. If we divide that by the force, 1935 newtons, that means the distance it can travel every second is 34 meters. Question 2. A car of mass 580 kilograms collides with the rear of a stationary van of mass 1200 kilograms. So I always think you really need to draw these out. 580 kilograms, 1200 kilograms. Following the collision, stationary van. So beforehand, the van is going at 0 meters per second, and the car is moving with some velocity u, which we don't know. So following the collision, the van moves with a velocity of 6.2 meters per second, and the car recoils in the opposite direction with a velocity of 1.6. So I like to draw everything going to the right and call that minus 1.6 meters per second to the right. Then it's just a fairly straightforward conservation of momentum question. So the momentum before, okay, let's be good, momentum before equals momentum after. So the momentum before is 580 u for the car plus 0 for the van. The momentum afterwards is minus 1.6 times 580 plus 6.2 times 1200. Okay, if you work that out, that gives you 580 u equals 6,512, which gives you u equals 11.2 meters per second. Okay, question 3. These are really good questions, I think, for making you think carefully about what's going on. The trouble is often with these graphs, people imagine a ball bouncer and they look at something like this, which would be a perfectly good graph probably for a distance time graph, but we're looking at velocity time graphs. So we've got a ball dropped from rest which bounces repeatedly. There's a lot in this, but actually getting the right answer should be fairly easy without having to go through all the complexities. It's got to start from the origin because it's dropped from rest, so it's not C. It then accelerates at a constant rate, so the line has to increase but increase at a constant rate because there's a constant acceleration. So it's not A and it's not D. Okay, this one, the acceleration is actually increasing. It doesn't actually mention here that it's we can ignore air resistance or anything, but it certainly can't be this way, because this way the acceleration is increasing. So that gets you to B really, and you only have to look at the first little part of the graph. If you want to understand it a bit more carefully, think about it. This is where it hits the ground, its maximum velocity. It then accelerates upwards, so the velocity changes very quickly from a big downwards number to a big upwards number. It then decelerates, so at this part of the graph it's going upwards until here where its velocity is 0 because it's reached the top again. And then once we've got to there, then we've completed one bounce. The ball has gone down to the ground and bounced back up to where it started from. I guess we can sort of infer from this that we are ignoring air resistance, both because the line is straight and it is also returning to the same height every time. So a nice question there. You really need to understand why B is the answer to that question. Okay, question 4 is fairly standard projectile question. I'm not sure now, but I have noticed in the past that the math department tend to answer these exact same questions but in a slightly different way. They like to work out how long it takes to reach the top. I tend to do it by just getting to the answer in one go of how long it's in the air for. So if you start with the equation s equals ut plus a half at squared, you'll notice that there are at the end, if we just look at the vertical part of this, because remember the whole point about projectiles is that the horizontal and vertical motions can be considered separately, they are independent of each other. So if we just look at the vertical part, the vertical displacement when it gets to here is 0, and you'll notice that there are two solutions here where this equals 0, and the simple one is when t equals 0. Well, when t equals 0, that's this solution, and when t equals some other number, that's this solution. So we do the initial upwards velocity, which is 25 sine 42, plus a half at, which is a half times minus 9.8, because we've taken the upwards velocity as being positive and the acceleration is downwards, t squared, and that gives you 16.7, which is this, divided by 4.9, which is this, is equal to t. We cancel out, sorry, I missed a t there, so we cancel out that t and that t, and we can divide by t as long as we know t is not 0, which is our other solution. So that gives you a time in the air of 3.4 seconds. Don't be confused between this s and this s, that's rather unhelpful, but can't do anything about that for you, I'm afraid. So 3.4 seconds is how long it's in the air for. Then you look at, okay, how far will it travel in that time? So we do horizontally. Well, horizontally, s equals ut. We can miss off the half at squared because there is no acceleration horizontally. So that means that it is 25 cos 42, which is the horizontal component, times the time of 3.4 seconds, and that gives you 63.4 meters. So that answer is D. Okay, a very standard question, very standard technique, so please try to make sure you can do those questions. There is another one coming later, by the way. Okay, which row gives two features of graphs that provide the same information? So we've got these. This is a displacement time graph, so the gradient of the displacement time graph is velocity. The area under velocity time graph is displacement. So those two are not the same. Gradient of a displacement time graph, again the same, so that's velocity. Area under acceleration time graph, this is the integral, if you push, this is the integral of a dt, and that is equal to the velocity, or the change in velocity probably I should say. Oops, so sorry. So that's that is also velocity. So that one is the correct answer, just to check the other two. So the gradient of velocity time graph, that's acceleration. The area under displacement time graph, that doesn't really mean anything. The gradient of velocity time graph, again, that's still acceleration, and the area under an acceleration time graph, that is velocity. Okay, or really I should say the change in velocity, but B is your answer. Okay, question 6. So two identical balls, X and Y, are at the same height and a horizontal distance of 25 centimeters apart. So again, there's always a lot of information in these questions. I would always recommend you to draw yourself a little picture, just a little scribbly sketch, just to get all that information onto the page, so you haven't got to try and hold too many thoughts in your head at the same time. X is projected horizontally with a velocity of 0.1 meters towards Y, so we go 0.1 meters per second in that direction at the same time that Y is released from rest. Both X and Y move freely in the absence of air resistance. What is the distance of the ball between the balls 0.1 seconds later? So the two crucial parts of this is, how far will X have moved horizontally? Well, that's just it's 1 second, so there'll be nice to you, this is just speed times time, so this is 0.1 meters per second, this is 0.25 meters, so we're now down to 0.15 meters because this has moved 0.1 meters in that direction. So the question is, where's Y? Well, the crucial thing to understand here is that Y will still be level, sorry, that's a Y, will still be level with X, because they will fall at the same rate. You'll have seen these sort of diagrams where you drop something and you take a picture every second and it looks something like that. You push it sideways and the sideways steps stay the same, but vertically each time it's still level. The horizontal gaps are the same. This is why you get a curved path, because of the vertical acceleration. So they will be horizontally level, but X will be closer to Y. Okay, question 7. So two bodies of different masses undergo elastic collision. So this is crucial in this question. This is an elastic collision. In the absence of any external forces, which row gives the effect of the total kinetic energy of the masses and the magnitudes of the forces exerted on the masses during the collision? So the total kinetic energy remains unchanged, because it's an elastic collision, and the definition of an elastic collision is that the kinetic energy stays the same. Remember, that doesn't always have to be true, but it does have to be true in this condition. So it's A or B. Then we look at this one, the magnitudes of the forces, the same on both masses. This is Newton's third law. If body A exerts a force on body B exerts a force of the same magnitude in the opposite direction on body A. So this one is right. Okay, these forces on the two masses are equal and in opposite directions. Number 8, so if you're struggling with any of this, you get a little freebie in number 8. If you can't do this, we're in trouble. Okay, because I'm hoping my year 10s could do this. Momentum has a direction, mass doesn't, velocity has a direction. So this is a vector, a scalar and a vector. So vector, scalar, vector. The answer is D. Please tell me you got that one right. Okay, number 9. So this is a much trickier one. So this is not like the earlier question, ignoring friction. This is sliding something down a slope. It's losing potential energy on the way down, and it's gaining kinetic energy, and it tells us the velocity at the end. But there is friction. So some of the energy that it's got here is being used against the frictional force to produce heat, and it's not all turned into kinetic energy at the bottom. So what we need to say is that the change in the potential energy has gone to two places. It's gone to the change in the kinetic energy plus the work done against friction. So our first job is to work out the change in potential energy. Well, we know this is mg delta h, so this is 2.5 times 9.8, and we're looking here for the vertical height of 3 meters. We can work out the change in kinetic energy because it starts off at rest, so that's a half mv squared, so half mv squared, so this is a half times 2.5. The velocity at the bottom is 5 times 5 squared plus w that's left over that we don't know. So this is 73.5 is 41.75, sorry, beg your pardon, try that again, is 31.25 plus W, and that gives you that the work done against friction is 41.75 joules. Then we've got to say, oh well, that's not what you actually want to know to the frictional force, but we remember of course that work equals force times distance, and we know the distance, so the force is 41.75 divided by the distance, which was 5, which gives us 8.35 meters, I think I've got, so 8.5, sorry, newtons, 8.5 newtons. Okay, number 10 is an impulse question. So the graph shows how the force varies with time. So we've got a force and a time, so we know that the impulse, which is the change in momentum, is the force times the time, but we haven't got a constant force here, so we've got to do a little bit of integration, but not mathematical integration, just finding the area under the graph. So we've got this part here, which is 4 times 4, we've got this part here, which is 6 times 4, and we've got this part here, which is a half times 6 times 6. Obviously you can use a trapezium formula or something if you want to. You add all that together and it comes to 58 kilogram meters per second, or newton seconds, that's the same thing. So the answer is D. Okay, number 11. So two spheres P and Q have the same volume, but P has a greater mass. So again, draw yourself a picture. We've got P and we've got Q, but P has got a big mass and Q has got a smaller mass. Sorry, try again. Yes, P has got a big mass and Q has got a smaller mass. And they have terminal velocities Vp and Vq, which row states the relationship between Vp and Vq and the reason. Well, when they're falling at terminal velocity, they've got a downwards force, which is mg. They've got an upwards force, which must be equal to that, but this upwards force depends upon the area and the velocity. So the areas are the same, even though I've not drawn them very well like that, but the areas are the same. So that means this must have a higher velocity to have a higher force. So Vp must be bigger than Vq. Okay, I've got to be honest, if I was guessing here I'd have thought it was one of the middle two, because there's two of those, only one of those. So actually you can go straight to this answer without reading the right hand side. But terminal velocity is unaffected by mass, we know that's not true, don't we? The mass of Q is less, so it accelerates more. I'm not quite sure what that means really. P reaches equilibrium at a lower terminal velocity. Well, that's not true. The velocity of P is bigger, and the opposite there. So D is the correct answer. The reasons really here are a bit strange. Okay, another momentum question. So a bullet of mass 10 grams is fired with a velocity of 100 meters per second from a stationary rifle of mass 4 kilograms. Consider the rifle and the bullet to be an isolated system. So this is a fairly standard recoil question, not recall, recoil question. So we've got before the total momentum before is 0. That's got to be equal to the momentum after. The momentum after has got two parts. It's got the bullet, which is 10 grams, so that's 0.01 kilograms times 100, plus the momentum of the gun, the rifle, which is mv, but we know that m is 4, so it's 4v. That gives you 4v equals minus 1, or v equals minus 0.25. So the recoil velocity, again no negative because it's saying it's recoil, so it's saying it's backwards. The recoil velocity is 0.25, so it's A or B. The total momentum, of course, the total momentum of the system stays the same, so the total momentum before is 0, so afterwards it's 0. So that answer is A. Okay, question 13 is actually a slightly easier version of that one we did earlier. So same technique, S equals ut plus a half at squared. So to reach the ground again, the distance is 0, the vertical displacement, we're doing this vertically. So we've got 25 sine 35 plus a half times minus 9.8 times t squared. I've done it again. Okay, t squared equals 0 again. One solution is t equals 0. The other solution is 25 sine 35 divided by 4.9. That gives you t, and that comes to 2.9 seconds. And this time they haven't asked you for the horizontal range, but you would have just done 25 cos 35 times that number to get the range. Okay, 14, so objects P and Q are initially at rest at time equals t equals 0. So the same force is applied to P and Q for a time t. So we've got force times time is the change momentum. So let's again just draw it out for ourselves. So we've got P and Q. We've got the same force for the same time. So the same change in momentum. But P has a mass 10 times greater than Q. So if this is m, this is 10m. But the change in momentum is the same. So the momentum at the end of this has to be the same. So this must have a velocity. If this has got a velocity of v, this has got a velocity of 10v, because either way the momentum is 10mv. If we look at the kinetic energy, so we know kinetic energy is a half mv squared, so that's a half times 10m times v squared, and this one is a half times m times 10v squared, 10v all squared. So this is 5mv squared, and this is 50mv squared. So if we do the kinetic energy of P, which is this one, divided by the kinetic energy of Q, that is 5mv squared over 50mv squared, which is 0.1. Okay, and 15, the last one. So the graph shows how the resultant force of F on a football which is initially at rest varies with time. So the force is increasing and then decreasing in a linear way. So which graph shows how the momentum varies with time? So if you think about the momentum, it's always increasing. This is a simplified model of how you might kick a football. The force will increase and then decrease, but all of this time the momentum is increasing. Remember, the momentum is the area under this graph. So if you were to look at how much the area is going up, it's going up by more and more and more. So this must follow an increasing curve. Okay, it's not increasing at a constant rate like A or B or even C. So straight away, really, again, even if you go into there, you already know it's an increasing curve like D, and then it's decreasing. Okay, so the height of this graph is equal to the slope of this graph. So D, sorry, it's gone off the screen, D is the correct answer.